All right, the name Rheindoll may sound familiar to you. It's a play on the names of two inventors, Joan Damon and Vincent Raymond. The Advanced Encryption Standard AES is a specification for the encryption of electronic data established by the U.S. National Institute of Standards and Technology, or NIST, NIST, way back in 2001.
Now you're the one doing history. AES is based on the Rendell cipher developed by two Belgian cryptographers, Joan Damon and Vincent Raymond, who submitted a proposal to NIST during the AES selection process. Rendell is a family of ciphers with different key and block sizes. For AES, NIST selected 3 members of the Rendell family, each with a block size of 128 bits, but 3 different key lengths. The first one being 128, second one 192, and the third one 256 bits.
A lot of numbers. Yeah, AES has been adopted by the U.S. government and is now used worldwide. It supersedes the Data Encryption Standard, as many of you know, or DES, which was published way back in 1977. The algorithm described by AES as a symmetric key algorithm, meaning the same key is used for both encrypting and decrypting the data. The most common SKC scheme used today, DES, or Data Encryption Standard, was designed by IBM even further back in the 1970s and adopted by the National Bureau of Standards, or NBS, now referred to, by the way, as the National Institute for Standards and Technology, as we mentioned, NIST, in 1977, for commercial and unclassified government applications. DES is a block cipher employing a 56-bit key that operates on a 64-bit block. So we're having a history lesson today.
Yeah, and DES has a complex set of rules and transformations that were designed specifically to yield fast hardware implementations and slow software implementations. Although this latter point is becoming less significant today since the speed of computer processors is several orders of magnitude faster than 20 years ago.
To say the least.
IBM also processed a 112-bit key for DES, which was rejected at the time by the government. The use of 112-bit keys was considered in the 1990s. However, conversation was never seriously considered.
Right. Yeah, it's a tough one to do. And on 2 important variants that strengthen DES are triple DES or 3DES, a variant of DES that employs up to 3 56-bit keys and makes 3 encryption or decryption passes over the block. 3DES is recommended over DES-X. DES-X, as you know, is a variant devised by Ron Rivest by combining 64-bit additional key bits to the plain text before encryption, thus increasing the key length then obviously to 120 bits.
Yes, and International Data Encryption Algorithms, or IDEA, is a secret key cryptosystem written by Shujia Lai and James Massey in 1992 and patented by ASCOM, a 64-bit SKC block cipher using a 128-bit key. It is also available internationally.
And along those lines, Blowfish is a symmetric 64-bit block cipher invented by Bruce Schneier, optimized for 32-bit processors with large data caches. It is significantly faster than DES on a Pentium PowerPC class machine. Key lengths can vary from 32 to 448 bits. Blowfish is available freely and intended as a substitute for DES or IDEA, as in use in a large number of products.
Yes, and Twofish is a 128-bit block cipher using a 128 or 192 or 256-bit keys. They are designed to be highly secure and highly flexible. Twofish is well suited for large microprocessors and 8-bit smart card microprocessors and dedicated hardware. It was designed by a team led by Bruce Schneier and was one of the round 2 algorithms in the AES process.
Right. Rivest ciphers, also known as Ron's code, Ron Rivest, as everybody know, was named for Ron Rivest and is a series of SKC algorithms. RC1 was designed on paper, but sadly never implemented. RC2 is a 64-bit block cipher using variable size keys designed to replace DES. Its code has not been made public. although many companies have licensed RC2 for use in their products. Described in RFC 2268. RC3 was found to be breakable during development.
And RC4 is a stream cipher using variable-sized keys, and it is widely used in commercial cryptography products. An update to RC4 called Spritz was designed by Rivest and Jacob Schultz. RC5 is a block cipher supporting a variety of block sizes, 32, 64, or 128 bits, key sizes, and a number of encryption passes over the data, described in RFC 2040. And RC6 is a 128-bit block cipher based on and an improvement over RC5. RC6 was one of the AES round 2 algorithms.
And RG3 is the quarterback of the Washington Redskins. All right. I think we got those all. The resources required for a brute force attack grow exponentially, as you know, not linearly with increasing key size. Now, although U.S. export regulations historically restricted key lengths to 56-bit symmetric keys, as with, for example, the data encryption standard, these restrictions are no longer in place. So modern symmetric algorithms typically use computationally stronger 128 to 256-bit keys. Now, there is a physical argument that a 128-bit symmetric key is secure against brute force attack. The so-called Landauer limit, implied by the laws of physics, sets a lower limit on the energy required to perform a computation of kT in 2 per bit erased in a computation, where T is the temperature of the computing device in kelvins, K is the Boltzmann constant, and the natural logarithm, or ln, of 2 is about 0.693.
You got all that right.
It's physics now. Yeah. We've got everything.
History to physics.
Yeah.
No irreversible computing device can use less energy than this, even in principle. Therefore, in order to simply flip through the possible values for a 128-bit symmetric key, ignoring actually computing to check it, would theoretically require 2,128 1-bit flips on a conventional processor.
No.
If it is assumed that the calculation occurs near room temperature, which is approximately 300 Kelvin, the von Neumann Landauer limit can be applied to estimate the energy required as approximately 1,018 joules, which is equivalent to consuming 30 gigawatts of power for an entire year.
So all this, Laura, everything you just said is equal to this number. And I don't even want to try to say it. It just represents more than 1/100th of the world's energy production, so you know it's massive, right?
Hard to comprehend.
Right. Yeah, the full actual computation, and that's what we're looking right here, and you can check each key to see if you have found a solution, would consume many times this amount. Now, furthermore, this is simply the energy requirement for cycling through the key space. The actual time it takes to flip each bit is not even considered in what you're looking at here, which is certainly greater than 0.
Yeah. However, this argument assumes that the register values are changed using conventional or unconventional set and clear operations, which inevitably generate entropy. It has been shown that computational hardware can be designed to not encounter this theoretical obstruction through no such computers are known to have been constructed as of 2014 or as we know by now. Modern GPUs are well suited to the repetitive tasks associated with hardware-based password cracking.
AES permits the use of 256-bit keys. Now, breaking a symmetric 256-bit key by brute force requires 2,128 times more computational power than a 128-bit key. 50 supercomputers that could check a billion 1018 AES keys per second, if such a device could ever be made, would, in theory, require about 3,153 years to exhaust the 256-bit key space. So that might take a minute.
Just a second.
Yeah.